Well, hello again, grade 12s. Mr. Jones here. I am going to try and finish off chapter 9 today, picking up with where we predict whether a redox reaction is spontaneous or non-spontaneous. Does it require energy to go forward? Non-spontaneous, or does it not require energy, Gibbs-free energy to go forward? Does it release Gibbs-free energy in the process? So it would then be spontaneous. And for some people that have taken biology, and I know that I've mentioned delta G values, Gibbs-free energy values, as being negative or positive, that is the ultimate determinant of whether a reaction is spontaneous or not. We're not going to do those calculations this year because we just won't have the time. But you should know that going forward to next year, first year university, where you'll likely cover that. So let's take a look at the schedule and see where we're at. So today we are still in chapter 9, and I'm going to, if I can just find my pen here, red pen, finish predicting redox reactions, and that is the last part of chapter 9. And I will take some questions from, not from your textbook, so that you have all the questions in your textbook to work on yourself. So let's take a look at the file that we are filling out together. Whoops, no, you can't see that yet. I almost made a mistake there. Okay, so I have to share that file with you. Here it is. Okay, predicting the spontaneity of redox reactions. So there are some general tasks that you have to do, and you have to figure out how to go about doing these things. And I don't think it's that difficult, but there is a routine that you have to learn, a set play, so to speak. You must remember what a reducing agent is, what an oxidizing agent is. Pardon me. Know that in every single redox reaction there is a reducing agent, and there is also an oxidizing agent. The reducing agent reduces something else. It gives electrons away to something else. That means the chemical or a group of chemicals, in fact, that are reduced sometimes will be receiving electrons from the reducing agent, and the oxidizing agent is the opposite. Okay, so in a mixture of many chemicals, there are many substances that can gain electrons and act as oxidizing agents. There are many chemicals that can lose electrons and act as reducing agents. So your job will be to predict and determine which chemical specifically is each of those. Which chemical is the reducing agent and which is the oxidizing agent? The strongest reducing agent and the strongest oxidizing agent, the SOA and the SRA over here. And once you've done that, then it's just applying this rule. It's called the spontaneity rule, and then you will know whether or not the reaction is spontaneous or not. So that's what we're going to do in the next few minutes. So I'm going to turn to tablet mode so you won't see my face. You'll see the top of my ceiling again and write down these definitions and then go through some of the basics with you. Okay, let me scroll to the top. I'm not sure why it went down one page. Okay. Let's so tasks. Know the relative reactivities of oxidizing agents and reducing agents. How do we do that? Well, your textbook takes you through a couple of pages to do that. And identify the oxidizing and reducing agents. We'll do that very quickly. Identify the strongest oxidizing agents, SOA, and the strongest reducing agents, SRA, and compare the relative positions, which is higher in a chart. And I'm going to give you a chart from the old textbook because I think it's easier to look at. It's a better chart. It's a more standard one. You're welcome to use the one in your textbook, but I will post the one from the book that I would have been using in class. So use the spontaneity rule. So here again, let me just choose my pen. What is a reducing agent? A reducing agent is a substance. Whoops. substance. Hey, no, don't do that. A substance. In fact, it is a reactant. Okay, it's a reactant in a redox reaction, but a substance that reduces another substance. And the other substance is also another reactant, but obviously a different reactant. And how does it reduce something else? It gives away its electrons by giving its electrons. E minus. Okay, giving its electrons. Okay, however, you should know that if something gives away its electrons, it is itself reduced. It becomes oxidized. So becomes itself. So the reducing agent itself becomes oxidized. Okay, and the oxidizing agent oxidizes. Okay, another. So it's the opposite. I'm not going to write it out in full. It oxidizes another substance. Okay, and itself, which means it takes away electrons from something else. It itself becomes reduced. Okay, so you should know that there are charts of oxidizing agents and charts of reducing agents ordered from top to bottom or bottom to top. So it's like an activity series where the strongest of each of those oxidizing or reducing agents in those charts is near the top. So over here, if you look at the metal activity series or ion activity series, you can have a reactivity or activity series to see which is the strongest in a certain respect. In this case, in terms of reducing or oxidizing, so reacting in a redox reaction, essentially. So over here, we have magnesium, nickel, lead, and silver. So four metals. Okay, and essentially what we are going to do over here is see which of these has the strongest reactivity, in the sense that which one loses its electrons most easily. So magnesium over here near the top, and silver is near the bottom in this chart over here. Bottom. Okay, that means over here, Mg loses electrons most, that's with an S, most easily. And at the bottom in this chart, because these metals have been ordered from top to bottom, in particular based on experiments to show which loses electrons more easily or less easily. Over here, silver would lose electrons with most difficulty. Loses electrons with most difficulty. Okay, and when we're talking about losing electrons, we're talking about the ease of oxidation. So this means if it loses electrons most easily, it is the most easily oxidized. Okay, and if it loses electrons with the most difficulty, it is that is silver. it is the least easily oxidized. Okay, and whichever chemical in a group of chemicals that are mixed together is the most easily oxidized will be considered the strongest oxidizing. Strongest is the opposite. This is where it becomes a little bit counterintuitive. The strongest reducing agent. The SRA. Okay, so I'm going to highlight that over here. Strongest reducing agent is the most easily oxidized substance within a group of chemicals. And the group of chemicals is those metals over there. And it's not always going to be metals that will be oxidized, but very often it will be metals as opposed to metal ions. Okay, let's move down here. Identifying the strongest oxidizing agent instead of strongest reducing agent. So the strongest oxidizing agent, okay, it says over here, oh, let me write it down, will gain electrons most easily. Okay, let me just count that up here. Strongest reducing agent will lose electrons most easily. Okay, from a mixture of different oxidizing agents or mixture of different reducing agents. In this case, now we're looking at oxidizing agents. So here, we're going to look at the positive ions that are mixed together. So here we will have a group of positive ions, 4 positive ions. Oops. I don't know why I'm having trouble with the basics of spelling this morning. It's perhaps that I'm a little still half asleep. So 4 positive ions. Okay, they're all can gain electrons. So silver has a charge of +1, which means it can gain 1 electron. Lead has a charge of +2. It can gain either 1 or 2 electrons. Nickel has a charge of +2. It can gain 1 or 2 electrons. Magnesium is monovalent. You know, it has, it only ever becomes +2, so it can gain 2 electrons. Well, they all gain electrons. And if they can all gain electrons, that means they can all become reduced. If they become reduced, that means they are therefore oxidizing agents. Okay, so if we order them from someone does experiments and figures out which of these 4 ions, silver ion, lead 2 ion, nickel ion, and magnesium ion, which of those 4 ions gains electrons the most easily? Ag plus gains electrons the most easily and is therefore becomes reduced most easily and is therefore the strongest oxidizing agent. Or the SOA. Okay, strongest oxidizing agent. So you will be given a list or chart that that has lists of oxidizing agents and lists of reducing agents. I want you to see that each one of these reactions, whether it's a metal or non-metal, so you can have over here, let's say we have Ag solid. It can change into, I'm going to use double half arrows here because now there's an equilibrium that can be reached and these reactions are reversible. A loss of electrons, gain of electrons. Ag solid, silver solid atoms can change into Ag plus ions, which are aqueous, so in solution, if one electron is lost. Okay, so the forward reaction here is an oxidation, half reaction, a loss of electrons, and the reverse is a reduction. Okay, and you can write those half reactions separately as oxidation, reduction, but in the chart you will see them in a single line. Oxidation in the forward direction, and reduction is the reverse of that. So both can occur. Okay, and you're going to see that in the chart that I'm going to show you. So I'm going to stop this share for the time being, and I'm going to share another screen. Oh, where is it? Where is it when I need it? I don't know. I'm going to have to go to my other mode. It should have been there. Okay. Figure out what's going on here. Exit tablet mode, yes. Where is that screen? Oh, there it is. Share this screen. Okay, so this is not in your textbook, it's in the old textbook, but you have this you have a table like this in your appendix of your textbook as well, except it's on 2 pages, not a single page. It's not so easy to look at. So this is the table of standard reduction potentials. And that's the file that I'm going to post on Google Classroom for you. So if you look at all the substances on, and now let me highlight this. I'm drawing on a computer screen that's wobbling. It's upright. Here, highlight this, oxidizing agents over here and reducing agents over here. Let me just write, oxidizing agents are anything on this. Oh, it's going to be messy. Let me delete that. Anything on so I'm going to divide this in half, these double half arrows. Anything to the left of the arrows, the double arrows, double half arrows, is considered an oxidizing agent. So left side. Anything on the right side of the double half arrows is considered a reducing agent. Right side. And you are supposed to know that an oxidizing agent or reducing agent can be a single substance, but it can also be a combination of substances. Okay, and that's where I want you to see this. So together, PbO2, SO4 2-, and those 4H+, will combine as a single. They're considered to be a single oxidizing agent. I need to put this in tablet mode. It's too difficult to write. Okay. Yes, tablet mode. So here, the combination is a oxidizing agent. Over here, and the same is true over here. Same is true over here. Okay, and over here, F- can, let me do over here, this over here, this over here. These are, so either individual AU solid by itself, or could be PbSO4 and 2H2O, a combination of those 3 particles. These are reducing agents. Okay. So know that. And you'll see that in the forward direction, okay, electrons are gained. Okay, so that is reduction. And in the reverse direction, okay, electrons are lost. And this is an oxidation. So I'm going to be referring to this chart as we go forward, and you may not see it on the screen, but maybe it's best that I do pop it up on the screen. Okay, so I may erase all the stuff that I've written here, so it's not so cluttered. Okay, so let's stop sharing that screen, and let's move on to the actual question that we should be working on. Over here, let's go back to this, share that screen. Okay, so we're back to here. So now I'm going to go on to the next page. Over here, what is way down there? Okay, so it says, notice above the oxidizing agents on the left side of the equation. Okay, so let me write down that equation for you. It's one of the equations that I circled on that chart that I showed you. So PbO2 solid plus SO4 2 minus aqueous plus 4H plus aqueous reacts reversibly to produce PbSO4, that's a solid, plus 2H2O, that's a pure liquid. Okay, so over here, this whole group of chemicals together is an oxidizing agent. Oxidizing agent. And together, this group of chemicals over here, the one PbSO4 plus the two waters is the reducing agent. And if you have that chart out in front of you that I just showed you, the table of standard reduction potentials, this is, it will see the second from the top. Okay, second from the top. And you'll see that there are, I've missed out something over here, plus 2 electrons. There are 2 electrons being gained. So note the position, left side or right side where the electrons are to determine whether or not a reduction reaction is occurring on, electrons are being gained, or if electrons are being lost, an oxidation reaction is occurring. Oh, look. So this is the second half reaction from the top. I made space for myself over here. Is this half reaction an oxidation or half reaction or reduction half reaction? It's oxidation half reaction in the reverse direction and a reduction half reaction in the forward direction. How do you know? Okay, E minus are lost or gained. Okay, in one direction or the other. Is the reverse half reaction oxidation or reduction half reaction? Reverse is an oxidation. Identify the oxidizing reducing agents. We have done that. So it says here, consider a series of half reactions where the SOA is at the top, SRA is at the bottom. Okay, and that's done in the chart where all of the oxidizing agents are placed on the left-hand side of the arrow. Okay, and the reducing agents are all on the right-hand side of the double arrows in that chart. So over here, the spontaneity rule is what we're aiming for, and to determine whether the reaction will happen. Does it just take place spontaneously, or does it not occur? Is it non-spontaneous? So if the strongest oxidizing agent is higher than the strongest reducing agent, the strongest oxidizing agent being one of the reactants, and the strongest reducing agent being another one of the reactants, then the reaction will be spontaneous. But if the reverse is true, the OA is lower than the RA, the SOA lower than the SRA, then there will be no reaction. So let's take a look at over here. Let's write Zn solid plus Cu2 plus aqueous. Okay, reacts reversibly to produce Zn2 plus aqueous plus Cu solid. Okay, that's a redox reaction. One of these two reactants is losing electrons. Okay, so zinc has to lose 2 electrons. Okay, and then copper must gain 2 electrons. So whatever is losing electrons is being oxidized. Okay, so that means it is the SRA. Okay. Let's delete that. Okay, and whichever substance or combination of substances gains electrons is being reduced, and it is the OA. In this case, there is only one, so it is the SOA, the strongest oxidizing agent. So the question then is, look at the chart, the table of standard reduction potentials. Is the SRA on a line higher than the SOA, or is the SOA higher than the SRA? So I'm going to take a look at that chart. Okay. So share screen. Let's go back to this chart over here. And so we are looking for zinc solid as the first reactant and copper 2 plus. Where is zinc solid? So you're going to have to strain your eyes a little bit. So the metals the metal solids will always be on the right-hand side. They're all reducing agents. So zinc will be somewhere over here. I'm going to scroll down and find it. Oh, and there it is, zinc. This is our SRA for that reaction that I just wrote out, the redox reaction. And then where is Cu plus 2 that gains 2 electrons, not 1 electron? Okay, so let's go down here. Is it lower? No, it's going to be higher, and that's a good sign. So we're going to see that copper plus 2 is over here. But look, this copper plus 2 is only gaining 1 electron, so it's not the copper plus 2 that we want. We go to another copper over here. This is copper plus 2 as well. Oh, this is not confusing, but it is now gaining 2 electrons. So it can gain the 2 electrons lost from the zinc. So they are both OA and OA. But whichever is higher is going to be the SOA. Okay. So our SOA is up here, and if I scroll down, we see the SRA is below. Okay, SOA is in a line up here, and it's probably about 20 lines higher than the SRA. So therefore, okay, I'm going to go back to the other screen. Hopefully it's cooperative here. All right. So this SRA, the SOA is placed higher in the chart, okay, which is the table of standard reduction potentials, placed in a line higher in the chart, in the table of standard reduction potentials. Okay, so the SOA is greater than or higher than the SRA. Therefore, this reaction is likely spontaneous. So the reaction of zinc with copper 2 plus to produce zinc plus 2 in copper solid is likely. I'm going to underline the word likely because you don't know for sure. It is likely spontaneous. And you can't say it is for sure until you calculate the delta G value, and the delta G, the change in Gibbs free energy, must be negative in order for a process, any process, reaction or otherwise, to be spontaneous. Okay, so I'm going to say understand the setup of a table of standard reduction potentials. So this one is from your textbook, and you can see that over here, decreasing strength of oxidizing agents. Oxidizing agents are on the left side of the arrow, left of arrows. Okay, and the reducing agents over here are on the right of arrows. Okay, that means the SOA, strongest OA of all of these combinations listed on the left-hand side, the F2, the Ag plus 2, the CO3, CO plus 3, and then the PbO2, 4H plus SO4, the either single chemicals or single, or combination or big combination of chemicals. They are all considered OAs. Okay, strongest oxidizing agents are near the top. Okay, they are near the top. Okay, if you don't get that over here. And then you can also have single reducing agents, single, or combinations. Okay, and I want you to see over here that the strongest reducing agents, okay, are near the bottom. Okay, and I'm going to say bottom right. This is very important. The strongest oxidizing agents are near the top on the left of the arrows. So you're going to have your chart out with you for the next example or two. This is turning into a longer video than I expected. Okay, and this is the chart over here. Look, SOA, top left, and down here, SRA, bottom right. Okay, left side of the arrows, right side of the arrows, you're looking two separate sides for different reactions. Okay, predicting the spontaneity of a redox reaction. So there's a whole routine over here, and there's a strategy in your textbook, and I think there are some charts to help you along, and it's a fair bit of work to contain all of that information in your head. And so I've listed some of the stuff for you over here that you have to know. You can also use what's in your textbook. Note what? Number one, all solutions contain a mixture of water and other stuff, one or more other things dissolved in water. So water liquid is there. And if it's there, it is a potential reducing agent and a potential oxidizing agent. It is a potentially reactive chemical species. All acidic solutions contain water and H plus ions. 3, basic solutions contain hydroxide, OH minus, in addition to water. Some oxidizing and reducing agents are combinations. Okay, we've seen that, like MnO4 and H plus together. By themselves, they may be an oxidizing agent or a reducing agent, but in combination with another chemical, they can also act as a single oxidizing agent or a single reducing agent. Some chemicals may act as either oxidizing or reducing agents, so H2O can either gain electrons or lose electrons. Fe plus 2 can either lose 1 electron and become Fe plus 3. It can also gain 2 electrons and become Fe solid. Same with copper plus 1, zinc plus 2, chromium plus 2. So many chemicals can either lose or gain electrons in a series of electron losses and gains. Number 6, any substance not present in the redox table, so the table of standard reduction potentials that I've shown you a number of times, you can presume that they are spectator ions, i.e. not react. Okay, i.e. will not be, i.e. Oh, let me say, I've said i.e. once, i.e. not react, therefore not the SOA or SRA. Okay, number 7, use the table of reduction half reactions, Appendix B7, the one in your textbook, or the one that I'm going to post, and keep it at your side when you're doing these reactions. So it says number 1, I'm going to do one of example number 1, probably 1A, and then number 2, I'll do another one, 2, I can't remember which one. I'll list it down here. So example 1A, determine whether the most likely redox reaction will be spontaneous. This puts together everything in chapter 9. This one question over here, and same with the next example. It is like a summative task. It's as many tasks put together. Determine whether the most likely redox reaction will be spontaneous. So you are given some information in 1A, and you can look above. It's written it out here in parentheses or brackets. A lead strip is placed in a copper 2 chloride solution. So here you must write out and identify what substances are present and whether each substance is capable of acting as a reducing agent or an oxidizing agent. And then you look up the table and determine, of all of the reducing agents listed, which is the strongest, and of all of the oxidizing agents listed, which is the strongest. And those two substances, or combinations of substances, will form the most likely redox reaction. So what a lead strip is Pb solid. Okay, it is placed in a copper 2 chloride solution. So copper 2 chloride solution, this is aqueous. This is CuCl2 aqueous. Wow. I'd be surprised if anybody could read that. CuCl2 aqueous. And what you're supposed to know in grade 12 is that aqueous ionic compounds don't actually exist. What actually exists are separate positive negative ions. So instead of copper 2 chloride solution or chemical compound, you actually have Cu2 plus aqueous floating around as a reactive species by itself, and you have these Cl minus ions also floating around as separate entities. And all solutions contain H2O liquid. Okay, so we have 4 chemicals that are potential oxidizing and reducing agents, and we want to determine which is the strongest. So we take a look at the chart, this table of standard reduction potentials. We see that lead is on the right-hand side, so it is, I'm going to choose another color pen here. Let's choose green again. That lead solid is on the right-hand side of the arrows in that table that I showed you. Unfortunately, can't show you at the same time here. It's hard to flip back and forth. So it is a reducing agent. Copper plus 2 is not on the right side of the arrows. It is, you can find it if you look very closely. It is in 2 places on the left-hand side, so it is an oxidizing agent. The chlorine minus by itself is on the right-hand side, so it is a reducing agent. And the H2O is, you'll find it on the right-hand side. It is a reducing agent. You'll find it by itself, but you'll also find it by itself on the left-hand side, so it is also an oxidizing agent. Okay, so now I'm going to flip to the other, to the chart, so you can see what I'm talking about. Let's find that. So where is lead? Lead is, I said, on the right-hand side by itself, over here. Okay, so it is an RA. How do we know? Because it's on the right-hand side. And what else are we looking for? We're looking for copper plus 2. It's on the left-hand side, so this is an OA, and it's on the left-hand side over here, OA. Okay, and then we're looking for a Cl minus. Cl minus should be close to the top over here. It's on the right-hand side, so it is an Ra. And then H2O is by itself over here, so it is also an Ra. But if we scroll down to the bottom of this chart, we'll also find H2O by itself without any other chemicals on the left-hand side, and it is therefore by itself, it is also an OA. Okay, so I'm going to stop this and go back to the other file with the question on it. So if you're wondering where I got these RA, OA, RA, RA, OA, well, that's where I locate, or you have to locate that particular chemical on either the left side or the right-hand side and determine whether it's an RA, right side, or OA, oxidizing agent, left side of the double arrows. So we're not done yet. So sometimes a combination of chemicals is in fact an oxidizing agent, or a combination of chemicals can be a reducing agent, and there is only one combination that you have to worry about in this list of 4 chemicals. The combination of Cl minus and H2O together, you will find on the right-hand side. So Cl minus can exist by itself as an Ra, and H2O is itself as an Ra, but together they are also an Ra. So I'm going to show you that if I can find it myself. Okay, so where is Cl minus and H2O? Cl minus, so Cl minus and H2O together over here, together, not by themselves, serve as a singular or single Ra. So that's where I'm getting that combination in this example right over here. So out of these RAs, how many RAs do we have? Pb, Cl minus, H2O, and the combination of Cl minus and H2O, we have 4 RAs. Which one of those 4 reducing agents is the strongest reducing agent? Well, all of them are on the right-hand side of the double arrows. Whichever is the lowest of those 4 reducing agents is the strongest. So lead, you will find, if we look again, is the lowest, SRA, lowest of RAs in chart. Okay. Okay, and then we take a look at the OAs. There are only 2 of them. There's a copper plus 2 and H2O. And out of those 2, which of those is the highest on the left-hand side of the chart? Well, copper is over here. So therefore, it is the SOA. How do we know? Because it is the highest. Okay, of OAs in the chart. Okay. So what is going on? The SRA is a reducing agent, so therefore it becomes oxidized, which means it loses electrons. The SOA oxidizes something else, so it in fact gains electrons. Okay, and there are half reactions for each of these chemicals. The SRA undergoes a half reaction, and it will be the reverse half reaction. You'll read it and write it, the reverse half reaction from the table. So take, what is it? Oh, I'm pressing the button on my pen. Take the reverse half reaction from table. So take the reverse half reaction from the table, and this will be the oxidation half reaction. And for the oxidizing agent, you'd find it in the chart, and you would take write out the forward half reaction. Forward half reaction from the table. Okay, and this would count as the reduction half reaction. Okay, so what is the oxidation half reaction? It is Pb solid changing reversibly into Pb plus 2, and in the process losing 2 electrons. And then was the reduction half reaction? It's Cu plus 2 aqueous changing, or sorry, gaining 2 electrons and changing, and that reacts reversibly and changing into copper solid. Oxidation half reaction, and this is the reduction half reaction over here. And now that you've identified the two half reactions, you can put them together, add them together, add together, and you end up with Pb solid plus Cu2 plus aqueous reacting reversibly to produce Pb plus 2 aqueous plus Cu solid, and that is the most likely redox reaction to occur. Most likely redox reaction to occur. Whoa. Okay, let's highlight that. Most likely redox reaction to occur. Okay, and PBS is the SRA, and Cu plus 2 aqueous is the SOA, and now we apply the spontaneity rule, and we find that in the chart, the oh dear, the SOA, I don't know why I must have hit a button. The SOA is higher in the chart than the SRA. Therefore, the reaction is spontaneous. Okay, and this is according to the spontaneity rule. Okay, and that's that. Okay, so that's one example. Let's do one more example very quickly. I'm not going to flip back and forth the chart, but I'll lay it out for you. You should have the chart out. So here we have to deal with way more chemicals. Example 1E, potassium permanganate solution. It's mixed with an acidified, so H plus, tin plus 2 chloride solution. So you have tin plus 2 separate from Cl minus, and solution, so H2O liquid as well. Determine whether the most likely redox reaction will be spontaneous. So we have to figure out what the reaction is, figure out, working backwards, figure out the oxidation half reaction, reduction half reaction, which chemical or chemicals are gaining electrons, which are losing electrons. But first we must list all the chemicals. So potassium permanganate is KMNO4 aqueous. And this is acidified, so H plus aqueous, tin plus 2, so this is SnCl2 aqueous. Solution means H2O liquid. Okay, so let's write out everything in full. So K plus aqueous. In the solution, we have MnO4 minus aqueous. We have, I didn't want to write the plus there. We have H2O liquid in all solutions. And since it's acidified, that solution also contains H plus aqueous. And tin 2 chloride, we have Sn plus 2 aqueous as a chemical present, and chloride, so Cl minus aqueous. So we have 1, 2, 3, 4, 5, 6. We have 6 chemicals instead of the 4 from the last example. Now we go through. We see if K plus is on the left side or right side. It is on the left side of the chart, so it is. Here I'm going to write in a different color. Okay, it is So it is an OA. It's on the left-hand side. MnO4 minus, you never find it by itself, but you do find it in combinations with other things. H2O, you can find it by itself on the right side or the left side. So if it's on the left side, it's an OA. If it's on the right side of the arrows, it is an RA. So it can be either one or the other, depending on the circumstances. In other words, what it is mixed with. H plus, you will find by itself on the left-hand side, so it is an OA. And SN plus 2, you'll find by itself on the left-hand side, so it will also be an OA by itself. Cl minus by itself is on the right side, so it is an RA. And now we look for combinations on the left side and other combinations of the 6 chemicals on the right-hand side of the arrows. And this in itself, just searching all those through all that tiny little text, may take a little bit of time. But to make things easier, since I've already done this, the combination of MnO4 and H2O together, you will find not 1-to-1 ratio, but you'll find them together in different numbers of MnO4 minus and H2O together with nothing else except electrons. You will find on the left-hand side. So together they serve as an oxidizing agent, and together MnO4 and H plus. That combination also you'll find on the left-hand side is an OA. And together you'll find H2O and Cl minus on the right-hand side. So they serve as an RA. Okay, and then SN2 plus, I missed out something. SN2 plus you find on the left-hand side, but you also find it on the right-hand side. It also serves as an RA. Okay, so you want to find, out of all the OAs, we have 1, 2, 3, 4, 5, 6 different OAs. Of those 6 different oxidizing agents, which is the highest on the left-hand side in the chart? And there is a combination of MnO4 minus and H plus. It's higher than all the other OAs. So I'm going to put an S in front of the OA and circle it, indicated that it is the SOA. And for all the RAs, we have 1, 2, 3, 4 RAs. Which of those RAs is the strongest? In other words, if you look at the right-hand side of the arrows, which of those RAs is the lowest in the chart? And it is the SN plus 2. So I'm going to put an S in front of that RA, circle it, and then write out the related half reactions. So the SOA, identifying that line, will give us the reduction half reaction. And it will be MnO4 minus, so I'm taking this directly out of the chart, aqueous, plus 8H plus aqueous. Okay, plus 5E minus. And that is what you'll see. Those are the reactants in that line, in that half reaction you'll see together. Produce Mn2 plus aqueous plus 4H2O liquid. Okay, and that is the reduction half reaction. The SRA shows an oxidation half reaction, or is itself oxidized, so that will give us the oxidation half reaction. Okay, so this is, so for the reduction half reaction, you take the forward, write it in the forward direction. For the oxidation half reaction, you write what you see in the reverse. Okay, so here, the SN2 plus aqueous, you will see on the right-hand side, and you read that half reaction backwards, and you see, well, it produces SN, that's not an SW, that's an SN4 plus aqueous, and 2 electrons are lost. Okay. So you can see over here that we can't simply add those 2 half reactions together because why? Well, you have 5 because you have 5 electrons being gained and 2 electrons being lost, and in every redox reaction, you must ensure that the number of electrons lost and gained is equivalent. 5 gained does not equate with 2 being lost. What do? We find the lowest common denominator between 5 and 2, and that is 10. Okay, so 5 times what is 10? You multiply this entire half reaction by 2, the reduction half reaction by 2, and the oxidation half reaction gets multiplied by 5. And you change all the coefficients according to that multiplication factor, and then you add together. And you end up with the balanced redox reaction. So the coefficients will now be, well, you add together everything on the left-hand side from the reduction and oxidation half reactions. Everything on the right side from both half reactions stays on the right side in the overall redox reaction. Electrons gained and lost will be 10 and 10. 10 electrons gained. And we'll have 10 electrons lost. Oh dear. And electrons. Oh, this doesn't like me. 10 electrons gained, 10 electrons lost. So the fully balanced redox reaction is 2MnO4 minus aqueous plus 16H plus, since we've multiplied by 2. And then the reactant from the other half reaction is going to be Sn plus 2. You multiply that by 5, so plus 5 Sn plus 2 aqueous produces 2Mn plus 2 aqueous, since we'll multiply that coefficient by 2, plus 8H2O liquid, since we'll multiply that coefficient by 2 as well, plus 5Sn4 plus aqueous. And 10 electrons lost and gained cancel out, so we don't write them here. We know for ourselves that this over here is the SOA, and that this over here is the SRA. And now we check the chart to see whether the SOA is higher than the SRA or vice versa, and we will find that the SOA is higher than the SRA, and that is applying the spontaneity rule. Therefore, the reaction is spontaneous. And that is basically, that is almost everything in chapter 9 put together. And that's the end of the video. I shall turn this off over here for all of you, and I shall bid you farewell till next time, and I will be in touch with you soon. Look after yourself, everybody.